Hi, everyone. I'm Sean with Trifacta. Here with Karthik, we're going to talk about what we call intelligent pattern profiling today. So I'm going to spend probably the first 15 minutes or so just kind of talking about the actual problem we're trying to solve, why we think it's important, and then we're going to demo some stuff we're working on at Trifacta, as well as some other kind of related work from the research community. And then Karthik's going to spend the second half of the talk talking about kind of the underlying algorithms and machine learning we use to derive the interactions I'm going to show you. So to get started, when we talk about pattern profiling, we're really trying to answer a few questions. So the first question is helping a user understand how their data is structured. And kind of embedded in this question is really kind of a second question that I think gets overlooked a lot, but it is all your data structured identically? And I'll talk a little bit about what that means. And then finally, it's important not only to understand kind of the structure of your input data, but ultimately the goal is to not just work with input data, but map it into some output data that's useful for whatever task you're trying to do. So we'll go through each of these in a little bit more detail. So the first one, how is your data structured? I think generally when people think of like very well structured data, this is something like this comes to mind. Nice rows and columns. People might call this kind of a relational format. You might see data like this in spreadsheets like Excel and so on. So this is obviously a very common input format, but probably just as important, this is usually the target output format for almost any downstream analysis task you're trying to do. So if you're working in analytic tools, reporting tools, machine learning tools, visualization tools, kind of across the board, generally speaking, most of them require data to be in a format that looks like this. But kind of more common, we're seeing data that's kind of semi-structured, so stuff like JSON or XML. This isn't as structured in rows and columns, but in some sense this data is already kind of very well kind of self-describing. So we do see some analytic tools that are able to work with data like this. And then kind of pushing it out a little bit further, you start getting into data that's structured more like log files. There's still some structure in here, but it's not kind of as self-describing as previous formats like JSON or XML. So kind of inferring the structure from these formats can be much more difficult for analytic tools and visualization tools. So moving on to the next question, is your data structured identically? What we've seen is that even in kind of well-structured data sets, you can end up in cases where if you kind of take a closer look, you see that there's actually some interesting substructure in the data that can make it hard to kind of standardize your values or make that data useful for analysis. So again, looking at kind of row and columnar data, oftentimes these columns will have kind of multi-structured or what we would call heterogeneous formats. So some common examples of this would be things like people entering their name in different formats, addresses in different formats, or phone numbers in different formats. Sometimes this is because a single source has the data stored in different ways. In other cases, it's because you're integrating data from multiple sources, so you end up with this kind of multi-structured format. And I'd say kind of on even when your data is not structured, the problem can be even worse. So dealing with things like log files, oftentimes you'll log kind of different types of entries to the same file. Or there'll be exceptions or other anomalies that make it hard to work with data across the entire data set. So these are the types of problems we were trying to solve in terms of kind of understanding the structure. But again, also mentioned before, the goal is not just to kind of understand the input, but map it to the desired output. And the problem really becomes, kind of if we were to summarize it, is that most of our tools, whether they're analysis or visualization tools, generally require the data to be tabular or homogeneous. And kind of unfortunately, increasingly data is increasingly non-tabular, or if it is tabular, it still kind of contains this kind of multi-structured, heterogeneous formatted data. So this is the problem we're looking to help solve. And really the goal is, how do we make this process more efficient, helping you go from this kind of heterogeneous, kind of diverse set of data into something that is easy to use in your analysis and visualization and reporting tools. So we kind of looked at the conventional approaches of doing this. I'd say kind of there's two that are the most common. probably by far the most common today still is using kind of hand coding, so writing scripts in languages like Java, Python, Perl. In the big data ecosystem, this could be Hive or Spark. Or using kind of visual mapping tools or log search tools or ETL tools. And I'd say kind of in either of these cases, what ends up happening under the covers, and most of the work is actually spent kind of defining complex regular expressions, complex patterns manually, which makes it really hard for people who don't have those technical skills to work with this kind of diverse set of data. They'll become kind of reliant on other people who have more technical skills. Or even if you have these types of skills, a lot of people don't want to spend their time writing regular expressions, and then your data source changes, and you have to update your regular expressions and your parsing logic. It becomes this very kind of tedious manual process. So the approach that I want to talk about today is what we call pattern profiling. And the idea is to combine kind of automatic pattern discovery with interactive visualizations. So we're going to try to discover the patterns in your data automatically, and then give you ways to interact with those patterns to perform operations like restructuring, reformatting, parsing information out, and so on. So before I get into kind of the pattern part of pattern profiling, I just want to talk a little bit about this kind of general concept that we call profiling. And the idea is to help users understand their data. And the way we do this is by presenting kind of visual summaries and visual kind of statistics of the data so that you get a general sense of what's inside of your data. So we'll go through a couple examples for continuous data or ordinal data. So data that's kind of numeric or dates or fields like that. There's some kind of standard visualizations for this using things like histograms, where you can very kind of compactly represent the distribution. You can very quickly kind of scan through the data, get a sense of how it's distributed, roughly what the min and max is, the median, are there outliers, and so on. So histograms are very useful for this type of data. A different way of thinking about profiling is kind of categorizing your data into bins based on data quality. So what percent of your data is valid, what percent is invalid, what percent is missing. So as an example, we show here kind of this green, red, and gray bar indicating the relative percentages of the different types of data. For string or textual data, especially kind of in the case of categorical data where you have a small number of categories or kind of low cardinality, you can again compactly represent this distribution by showing maybe just the prevalence or the frequency of unique values inside your data set. Where these types of histograms traditionally start breaking down is when you get into kind of text-heavy data or data that has a lot of unique values. So here we're showing kind of a log format or semi-structured format. And you can see at the top we're still trying to show the number of unique values, but as you get up into the hundreds or thousands of categories, it becomes really hard to kind of represent this data. You can fall back on things like showing just the top K values or the most frequent values, but then of course you're losing a lot of information that might be relevant for your analysis. So this brought up the idea of, is there some other way to kind of group your data or bin your data so you get a high-level sense of what's in it and allows you to start working with it? So the idea that we're going to talk about today is one way of grouping it, which is through kind of what we would describe as the substructure or the pattern representing that data. So up here we're showing, looks like phone numbers, and there's a few different formats, and the idea is that if you have multiple formats of phone numbers in your data, can we kind of automatically discover those and then group your data into kind of subgroups based on that structure? So when we put all this together with pattern profiling, kind of again, the goal is, can we automatically detect and display these formats and these patterns within a column, and then we're going to kind of visually summarize them on screen so that you can begin working with them. Again, the goal being users can quickly kind of understand what those substructures are. Are there any anomalies? Does everything follow a consistent structure? And so on. And then kind of, perhaps more importantly, not just display this information, but provide a starting point so that you can then work with those subsets of records and do whatever you need to do with them so that you can move on with your analysis. And the how, I'm just going to brush over this at a very high level, and then Karthik's going to get really into the actual details of how we do this. But kind of the general approach we take is we're going to cluster records into meaningful subgroups, then allow users to interact with those subgroups, And then based on those interactions on those subgroups, the system will suggest transformations or kind of rules that you can apply across your entire data set. So I want to talk quickly. There's actually been a bunch of related work in this area. Some of it's been kind of purely on the algorithmic side, and Karthik will talk about that when we get into the algorithms. There's also been work in the past that I want to highlight before jumping into our interface, just to show you kind of things other tools have done and other interactions. So this is a tool called Potluck. That was based out of MIT, or came out of MIT about 10 years ago, actually. And here, again, they're working with this idea of phone numbers. And you can see here, based on the structure of the phone number, they kind of divide it up into 3 groups. So this is one way of kind of visualizing these kind of subclusters. And now I'm going to get into a demo. And first, before we get into some of the stuff we're doing at Trifacta, I actually want to show you a little bit of the interactions they have here to give you a sense of the things that you can do with this underlying technology. So this comes out okay, but you can see kind of they have the numbers divided up based on their structure, and then the idea is if you want to do operations like reformat or delete values, you can kind of operate on these individual groups and apply rules over the entire group. So this allows you to very quickly, oops, is it not playing? Oh, there we go. So yeah, here we go. We start seeing the cursor here moving. You can start kind of applying these bulk operations, like in this case, adding a value and kind of reformatting these values in bulk. And in this case, that's fine. That was, I think, what I wanted to show anyways. So that's one technique for working with this data and kind of applying these techniques. Okay, so now I'm going to jump into Trifacta. I'm not going to demo most of the tool, just the parts needed for, or not going to demo most of the product, but just the parts needed to kind of make these points. So first here, we're kind of showing like a standard grid view. We have kind of raw values in the grid, and then additionally, we're kind of profiling all of the columns at the top. So the profiles, as I mentioned kind of on the previous slides, are based on data types. So up here, we can see we have an event ID. This is one of those strings with really high cardinality, so the profile, as kind of mentioned before, isn't as useful. It just shows that there's a lot of unique values. They all occur about the same amount. If we look at email, you get kind of a similar structure. The profiles start being more useful when you get to things like the access time, where we can see here kind of the distribution of how many people are entering the site based on kind of rolling weeks here, so you get a nice breakdown. For low cardinality text, like the manufacturer of the device, you get a very quick breakdown here, and this histogram is actually quite useful to see kind of the relative distribution. Samsung appears the most often, followed by Motorola, and so on. So I want to now dive into, again, let's go back to the example of phone numbers. Here we have a phone number column. Again, we'd expect a lot of unique values across our users in the phone number column. So again, this column becomes a little less useful. So instead, what we're going to do is bend the data a bit differently. So if we go into our profile options, we can choose, instead of grouping by raw value, we're going to group by pattern. And now this histogram will update, and you see there's only a few different categories. And as you scan across the categories, you can start seeing, okay, there's one category that's very popular, which is 3 digits, followed by 4 digits. There's another one that looks like it contains an area code and maybe a country code, and so on. And you can start scanning and get a sense of that breakdown based on that substructure. As I mentioned before, we want these charts to be interactive so that you can actually do something with the data. So the idea is, as you select these groups, we'll give you suggested transformations of how you might want to handle structures like that. For instance, you might want to only kind of keep those values. You might want to delete those records, or you might want to extract certain information out of them. So we can zoom in on just the transformed rows here. In this case, the rows that we would keep based on this suggestion. And very quickly you can kind of scan through, and as you select other groups, you can drill down to just that subset of records that you would like to work with. In this case, maybe we're interested in doing an analysis based on area code. So if we go back and we see, there's certain records that don't have an area code, maybe for now, since we don't have a sensible default, we can just choose to delete those records. And you'll see the profile updates. There's no longer records that kind of have that substructure. So let's go into maybe a slightly different example in this case. One of the things we might want to do actually is kind of examine these patterns in a bit more detail and kind of have a little more real estate to work with them. So we can go into kind of a view dedicated for working with these patterns. Here, and again, we see kind of a breakdown of the patterns, some example records, and the count of those records. Additionally, as we are working with these patterns, in addition to just wanting to delete these records or so on, you might want to actually work with some of these subfields. So in this example, as we mouse over, we can see there's the area code here. It's kind of linking back to the actual pattern itself. So we can see there's this kind of 3-digit area code. We might want to extract that into a new column so that we can just kind of analyze the area code in another tool. So let's go ahead and select that. And just as before, we'll get suggestions down below of dealing with that type of data. We see here in the bottom left, there's an extract suggestion that looks interesting, and we can preview this in the grid if we want to see what it's doing. And it's doing what we'd expect when we selected that field. It's actually extracting that area code out into another column. Unfortunately, actually, when we scan through, it's pretty close to what we want to do, but we can see there's actually area codes in these other columns that we'd also want to work with. So one of the nice things and one of the ideas here is that the system can't always 100% guess what you're trying to do, but maybe you can give it more feedback, or it can recommend multiple alternatives that you could then apply to your data. So we can scan through. We see that there's actually a second suggestion here that we can select. And now when we scan back over the data, you can see it's generalizing a bit more. And in this case, it actually is performing what we like. And now we're extracting out area codes from all of these columns. And we can enter that into our data. So I want to just show a couple more examples to give you a sense of some of the kind of design issues and some of the issues when you're trying to design an algorithm. And Karthik will actually touch on this in a bit more. Let's look at a couple other columns and the profiles that come out of it. If we go into user email, we can see the first kind of level of pattern the system recommends is email. Which actually is what it is, so that's good. But it might not really be at the right level of granularity of what you're looking for. And this is always kind of the issue when we're trying to automatically infer structure, is you can kind of overgeneralize, or you could be a little too specific. So one of the things we wanted to enable in this system is being able to kind of navigate this level of granularity and have the user give feedback, and the system kind of try to predict a better level of granularity based on this feedback. So here we can zoom into email, and we see now we get kind of additional substructure. In this case, you could argue, well, maybe it's kind of too specific now. Maybe we don't care that it's 4 lowercase letters. We just care that it is lowercase letters. So these are some of the challenges that arise when kind of trying to build this type of system. And Karthik will go into some details on how we kind of approach that problems in a way we can try to improve the system through more data. So I just wanted to give one more example. This was dealing kind of with rows and columns and kind of substructures within rows and columns. But we also can apply this to kind of more or less structured data like log files. So here's an example of a log file. Again, you can see there's, in this case actually some values that appear a lot more than others, but in general there's a lot of unique values. As we scan through and go further and further down, you can start seeing some of the other structures that are in this data. So again, this profile is not that useful for working with the data, but we can do the same thing as before and kind of change the way, instead of looking at the unique values, try to find the interesting substructures in these kind of heterogeneous log files. So again, we see the histogram updates. As we'd expect, since a lot of the values are the same, a lot of them follow the same structure. If we're interested in those values, we can kind of zoom in again on just those values. We see it's these ones that kind of start with debug and are quite similar. And then as we scan across, you can start seeing the different types of records that are in here and cluster these together and then apply kind of similar techniques before to either extract relevant information or kind of filter down to a relevant subset of records. So with that, I'm going to pass it over to Karthik, who's going to talk about some of the algorithms we use to actually power the interface.
Thanks, Sean. Before we jump into the technical details, I'd like to give you guys a little bit of the product and user experience thought that went into designing this sort of thing, and then it'll help us inform what sort of technical implementation we choose. So one question that's really important is understanding the user's mental model of what a pattern is. A pattern consists of tokens. So tokens are the atomic unit of a pattern. And you can combine tokens in various lengths. So for example, you can add 4 characters and get a token. Tokens obviously vary. You can have digit tokens, alpha tokens. You can have composite tokens like alphanumeric, which is a digit and a alphabetical character. And the other important thing to note is that patterns carry positional information about tokens. So they're an ordered set of tokens. And ultimately, what we want to do, which Sean pointed out with the email example, is we want to help the user get some sort of semantic understanding of what's in their data. Not just like we have a bunch of numbers and digits, but we have this object in our data. So here's an example of an actual piece of text. This is an address. You can see that it has 2 sort of numerical fields, house number and, I should say zip, but it has a house number and zip. And then it also has some alphabetical and delimited fields like street name, city, and state. And we can come up with some sorts of rules to define what what your house number is and what your street address is and what your city is. And then by combining all of these, we would get the American address. That would be another semantic element. So let's look at like this brief text example. And the area in brown is actually the shared structure across the 5 rows. But you can see that we have a general pattern which describes all 5 rows, and it has some optional elements. And then we also have the top 2 rows and the bottom 3 rows. And they all share this sort of highlighted thing called the product code, which is what the analyst might want to work on. So given these sorts of different specifications, the analyst might actually want to extract the product code. But we'll see that we quickly run into issues with hierarchical or nested pattern structures. So we have this top level thing, which is sort of a generalization of the bottom 2 things, but it's hard to understand. And as you get more nested and deeper structures, we need to enable analysts to sort of slice through the different levels from most general to most specific. So what we want to do is take these sorts of low-level representations and then cluster them into higher-level representations. And then we want to allow the analyst to navigate the higher-level representations. So we might want to like start over here in the top corner with the things and then cluster them into numerical 6 or numerical 7. And then we want to go towards more concrete things as well so that analysts can effectively navigate the pattern hierarchy. And one of the key things which Sean demoed is example data. So example data can really help users understand what it is they're seeing at different levels, because it allows users to connect the examples and the literals that they understand to the actual token representations. And we actually imagine that the user journey starts off at some sort of abstract representation, then they interact with concrete examples, and then they move between abstract and concrete, slicing at different levels of the tree before they finally get to some sort of acting. A lot of the inspiration for our technical details were taken from PADS, which was work done in the 2000s. And PADS itself is a data description language. And it was originally conceived as a way to like create formats. So you can see like some different types they support and different structures they support. And then when you write a format, you can use this to process and structure data. And I've like listed a bunch of references if you guys are interested in this. The key work that we actually try to build on is a paper they released called From Dirt to Shovels. So basically, they want to take this unstructured data and generate the full pad specification from it automatically, so without any user input. So they take this unstructured data, they tokenize it, they attempt to discover some sort of structure within it, and then they refine this structure until they get to some sort of minimal specification that they can use to process further data of the same type. And this is very similar to what we want to do. We have this sort of or semi-structured data, ad hoc data, and we want to discover the pattern structures within it and present it to the user so that the user can navigate these pattern structures to perform some sort of action on them. So the first step is to define the sorts of tokens that we care about and the hierarchy of tokens that we care about. So you can start off with the most general sort of token, which is like the wildcard or any, which in regular expressions would be like the dot. And then you get more specific, so you get things like semantic tokens, like email, which convey some sort of semantic meaning to the user. And then you get character level tokens like alphanumeric and alpha and digit. And then finally you have literal tokens like slash and at. And one thing to note is that there are actually parent-child relationships across these tokens. So for example, the delimiter character level token might be composed of various literal tokens. And email is composed of a delimiter and alpha, for example. This is just like an example of how you can take 2 or 3 input records and then compose them, tokenize them into different representations. We'll just use some sort of standard lexer like flex. And we tokenize in order of priority, so you'll want to give precedence to the more complex things, the things with longer regular expression length. If you encounter any errors, you can just treat the any token as that token. And one important thing to note is that you want to make sure that you maintain the semantic to literal hierarchy. When you're navigating, it'll make it easier for subsequent pattern aggregation. So this is really the important part, right? Once we've lexed and we've generalized these basic leaves in our tree, how can we aggregate them and determine how to combine and generalize them? So the first thing we're going to use is something inspired from PADS, structure discovery, to figure out what are the possible structure and union tokens. So basically, structure discovery is given a set of tokens S, which we've already defined, and some data, so a bunch of records that we get, which tokens are the union tokens and which tokens are the structure tokens. So if you have 2 tokens A and B, a union relationship implies A or B, so that in any given record, A is present or B is present. And a structure relationship implies that both A and B are present. So typically, union relationships encode some sort of branching logic in heterogeneous data, and structure relationships, as the name implies, they imply shared structure. So you want to find the structure across all your records. This is some pseudocode if you're interested in actually running through the algorithm. But essentially what you can do is, for each token, you can generate a histogram which calculates the number of matches of that token over D. And then for each pair of histograms, so for each pair of tokens, you can compute some sort of relative entropy measure like the KL divergence. And then we can run some clustering, hierarchical clustering, using this entropy measure as our distance metric. And this will give us a bunch of clusters. For each cluster, we can determine if the histograms have high coverage. If the histograms have high coverage and narrow distribution, this means that they're structure tokens. And if the histograms have low coverage and wider distribution, this means they're union tokens. And we can get some sort of intuitive understanding of this. If the histograms have lower coverage and wider distribution, you can understand that they have union relationships, because in unions, you have some sort of branching logic. So you'll want these tokens to appear in some of your subsets of data and others of your subsets of data, but not all of them. On the other hand, if we're looking at structure tokens and they're shared across all of your data, you'll want high coverage and narrow distribution, so lower variability. So in this figure, you can see that A through E are structure tokens. They all have high coverage and narrower distribution. And F and G are union tokens. So they have lower coverage and they have wider distributions. Once we figure out what our structure and union tokens are, we can then align the tokens in our patterns. So align the token sequences using something like longest common subsequence. And we can take into account the union and the struct tokens when doing this alignment. And then, if we have any non-aligned tokens, and these tokens differ, we can use token hierarchy that I was talking about earlier, where we understand the relationships between tokens at different levels. So here's like a really basic toy example. And let's say we have these 2 patterns that are showed at the bottom. We have upper foo and lower bar. And then we've structure discovered on our data, so we know that upper and lower are a cluster, and foo and bar are a union cluster. And so we align. And then we can use a token hierarchy. So we know upper and lower make alpha, and foo and bar make foo bar. So we can combine upper and lower into alpha, and foo and bar into foo bar. And finally, once we've combined our tokens into one pattern, what we want to do is score it so we know how well our aggregation did. And there are a variety of criteria that you might want to use to score. So you'll definitely want to keep track of the number of wildcards and clean stars, so like the dot star sort of stuff. You want to keep track of the number of semantic tokens that you use, the number of basic tokens you use, and the number of struct tokens you use. And we'll want to penalize the wildcards and the clean stars because they indicate that we're using too much optionality. So if you have some pattern like any star, num, this is really confusing for users because they don't understand what it maps to in the data. We'll also want to penalize semantics because we don't want to roll our data up into semantic tokens too early on. We want to maintain a full pattern tree, like a rich pattern tree without pruning. Conversely, we'll want to reward basic tokens because we want to maintain this rich pattern tree. And then we'll definitely want to reward the presence of struct tokens because this means that our pattern tree has good shared structure. You'll note that there's a bunch of free parameters here, which we can just arbitrarily set to achieve good numbers. But as Sean was alluding to, we can also tune these by getting feedback from our users. So now that we understand how to combine two patterns, we can talk about how to generalize this to all the patterns that we've generated from lexing our records. So we can just do a sort of pairwise pattern aggregation. So for each pair of patterns, we combine the patterns and we get the parent and the score. Then we'll sort these scores in descending order and take the disjoint set of all parents and accept them into our next round of aggregation. And then we keep repeating this aggregation until only one pattern is present. And then if you kind of squint and look really closely at this, this is just basically another way to do hierarchical clustering, except that we can keep track of the tree relationships between the different nodes so that users can traverse them later on. The last part is how can we generate interactive examples, since we want to present the example data to the users. So once we have these candidate patterns, as the users slice across the pattern tree, we can just run some conditional aggregate queries. So we'll take each record, we'll match it to its pattern, and if no pattern is found, we'll match it to other, and then we can just aggregate over these records to present examples. And then to get the nice interactive highlighting experience, we can just use capture groups. So the nth token corresponds to the nth capture group, and then you can see where it matches up in the regular expression. So that gives you like an understanding of the general process we followed from product and user experience discovery to technical implementation. And now I'll try to briefly talk about some extensions. So one thing I sort of alluded to earlier, but we'll talk about more in detail now, is about injecting supervision. So almost everything that we've done so far has been unsupervised. So it's been clustering. There have been like some information theory sort of concerns like relative entropy, but we haven't really modeled anything yet. And the first example is pretty straightforward. So we have all of these free parameters where we score our aggregations, we score which tokens are unions and which tokens are structs, but it's all just tuned by hand. But we can easily improve these by using some sort of human-in-the-loop feedback. So we know that users are interacting with these sort of visualizations, and we know that certain sorts of visualizations drive them to succeed. So they can successfully extract data, they can successfully standardize data. So by taking this sort of success metrics from them, we can improve our aggregation scoring and present them with a better visualization when they start off. And secondly, there's this thing called the token ambiguity problem. So if you have something like 192.168.2.255, it's hard to know whether it's an IP address, whether it's a bunch of integers supported by periods, or whether it's a bunch of floats. And some of the follow-up pads work actually talks about how you can understand what token corresponds to what literal in a better way. And so Shi et al. In their pads work, they propose that you can train hidden Markov models and other state models, like a hierarchical SVM, to traverse all the possible lexing and tokenization paths, and then pick probabilities based on pre-labeled data. So if we go through and label these by hand, and we say that this is an IP address, then we can train some sort of state machine model to figure out what the best path is. And the last extension I'll talk about really briefly is improving performance. So what we've built works really well for hundreds, thousands, those sorts of magnitudes. But when you get into millions or billions of records, lexing and structure discovery is really, really expensive. Because basically what you're doing is running regular expression matches over and over and over again on records. So there are definitely considerations for how to optimize this, either by doing some sort of approximate method like sampling over your data, or by doing something different rather than just running brute force regular expression matching. Cool, so that generally ends our talk. I'd like to give some thanks to all the others who worked on this, including Mike Minar, Athena, Anish, Lionel, and all the others at Trifacta who helped us build this sort of great end-to-end experience, where we can take these pattern structures that we've discovered ourselves, present them to the user in a rich way, and then allow them to interact across different levels so that they can get actionable insight on their data. And we'll be at booth 823 if you guys want to talk to us about patterns or profiling or data wrangling or anything like that. And I'll open it up for questions. Yeah. Or is?
No, I was just about
Okay.
to ask a question. Do you have it?
Yes.
Yeah.
So where are you performance-wise then? How do you fare on millions to billions of
Yeah. So the real problem, we don't perform any worse than having to run regular expression matches across all of these records. But we find that even on smaller data, the majority of our time is actually spent on lexing. So once we've generated the leaves of our tree, pattern aggregation and rollup happens very quickly. So about 95% of our time is actually spent figuring out how to go from raw records to the lexing. And so we need to figure out some alternatives for how to improve this process.
So can the user have an interactive experience with, say, millions of data points?
Yeah, so currently what we do is we would subsample your records, and then as you discover that you have other patterns which are not found, you can drill into those. Yeah.
So for big data sets containing like millions of records, so what is your approach for those? You mentioned something about that.
Yeah, so we think that probably the best way to tackle this problem in an interactive way is to allow users to choose whatever sample of data they want, and then they should operate on this sample so they can visualize all the patterns and interact on this sample and generate transformation steps from this sample, and then they can take these transformation steps and apply them to the whole data. I don't know if there's much value immediately in running the sort of clustering approach across like petabytes of data. Arguably, users, when they understand what subsamples of their data they want, they can just ask for those subsamples and then run this clustering on those subsamples, and then generalize by applying transformation steps.
So you're meaning like a top K and then sort of feed that top K to the...
Sure. Yeah, like a top K, some sort of stratified random sampling, any sort of approach that lets users better pick what data they want to operate on.
Yeah, one thing I didn't touch on in the demo was we're working with records, working on the patterns, and all those things I did were basically generating rules or reusable logic. That logic can then be translated to any system. So for us, we translate it to Spark that you could run in a distributed setting. So you can kind of separate out where are you learning the patterns from then where are you applying the rules. So if pattern detection is expensive in certain cases, which it is, you can work on subsets. If we spot that there are records that don't match to any of the rules, you could then kind of iteratively work on those to refine your rule, but then always kind of generate logic for doing the transformation that would apply across arbitrarily large data, whatever a cluster could handle or a cloud computing environment could handle.
I have another question.
So does the software actually generate like a log of the transformations that the user actually applied? They can then take that, for example, to another data set?
Yeah, so we try not to get too much into what we're doing. We're trying to focus on just the pattern profiling, so we can talk about that after. But yeah, generally, everything you do in our product will generate what we call wrangle. It's basically logic in kind of a high-level data transformation language that we can then cross-compile to different runtimes, including Spark, MapReduce. We have our own in-memory engine as well that we can run client-side called Photon. and more recently Apache Beam to run in a cloud or Google cloud environment.
Do you want to ask a question?
Yes. So I've not used the solution before. Is it meant to be used in standalone fashion, or do you expose any APIs that we could potentially, pull into our own web-based solution?
Yeah, so we have a whole suite of APIs, both kind of for running those jobs. So that logic that you could reuse across data sets, we expose an API to that, so you could kind of run it headless, that logic, on a cluster or on new data as it comes in, as well as kind of a suite of standard APIs for object creation, accessing metadata, that type of stuff as well.
Yeah.
All right, let's give a round of applause for our presenters today.